Welcome everyone to this, I guess, Stats Society Canberra April online meeting. My name is Francis. I'm the current president of the Canberra branch of SSA. Just a little, I guess, two minor points of housekeeping before we begin. The first one is that this meeting is recorded and actually will be made available to SSA members afterwards through the appropriate outlets, and so please keep that in mind. And the second one, which I think all of you are actually heeding to, is that essentially, unless you actually have to speak, it'd be preferable if you actually muted your microphone, just so to try and minimize the amount of background noise. Okay, so with that out of the way, it's a great pleasure to be able to introduce Professor Howard Bondell. Howard is a professor of statistical data science, the co-director of the Melbourne Centre for Data Science, as well as the deputy head for the School of Maths and Stats at the University of Melbourne. He's currently supported by a future fellowship from the ARC, and has a wide array of research interests, including model selection, robust estimation, regularization, Bayesian methods, and all aspects of modeling and handling uncertainty in statistical and machine learning approaches. So today he's going to be talking about variable selection for decision-making in individualized treatments. Thank you, Howard.
Thank you, Francis. So it's great to be here, at least virtually, and don't mind my background. As Francis knows, I've made my office my son's room since there's multiple people here working from home. And so you can see the colorful background, including a pet bearded dragon that my son has in the back there. So let me pull up my screen to share the screen. And, all right, everybody see that okay? Yes, I guess we're all good. All right. It's weird doing this thing online where feedback is a bit different, so we'll see how things go. So this talk is it's non-technical, so just kind of more of a background, kind of the problem and some ideas that we've come up with. And so we're going to talk a little bit here about variable selection for decision making, which we'll see is a very different target of variable selection than the typical variable selection methods. And the decision making here is for personalized medicine, individualized treatments. So there we go. Okay, so for just a quick outline, so I'll talk again the title for variable selection for decision making in individualized treatments. So the first thing I want to talk about is just a very quick background. What do I mean by individualized treatment or personalized medicine? And then I'll talk a little bit about what I mean by an optimal decision rule and how to construct an optimal decision rule. And then based on that, I'll introduce our idea of a test-based variable selection for decision making. And then I'll apply it to a clinical trial. So just to give you kind of this little graphic that I've pulled off the internet. This gives you a little idea of what I mean by personalized medicine. So if you look on the left, it's kind of the standard treatment, right? The green treatment is best for everybody, best overall on average. So I give that to everybody. And if you notice that the 3 people that are green, they do really well. So they get a positive effect. We're assuming here is positive is good. So everybody, the 3 in green do really well. The other 3 that have a little bit of green just have kind of no effect. And the purple one over here does really poorly. Ideally, we want to know that. So we have these patients and we do some diagnostics and have a bunch of candidate variables we take on them. And based on those candidate variables, then we were able to detect, okay, this first subset over here, they're going to benefit the best from the green. This middle one is going to have a combination and they'll benefit. And then the purple one will have purple and everybody's going to get a great effect and everything's perfect, right? So that's what I mean here by individualized treatment or personalized medicine, right? We want to find these biomarkers or variables or whatever they might be to be able to make these decisions of which treatment to give. Okay? So again, the idea is that same treatment's not always going to be best, but how do we make that decision? Which treatment should be given to which patient? And again, it's going to depend on some characteristics. And so, for example, it's going to be age, sex, maybe some long medical history, a bunch of information about that. Maybe we have genetic information and all sorts of other things. But obviously, collecting and storing all of it is going to complicate the decision process, and it's going to also add cost and variability, right? So we want to be able to pick out which variables are going to be relevant, right? And so the goal is to identify the characteristics that are important for the treatment decisions. Now, I'll give this just a motivating example here, and we'll go back and look at this study at the end. So this particular study, it's not that recent. It's 10, 15 years old, but just gives you some idea of what we're looking at. So it's a randomized double-blind trial to compare treatments in HIV patients. So this is a smallish data set. There's only 16 covariates, but the idea would translate to others. It is large in the sense that it's a large trial. It has 1,100 patients. Okay? And in the 16 covariates, we've got age, sex, there's a previous treatment history, and then some other, and we'll examine that a little bit later. So this just gives you a kind of a basic background. And so the predominant treatment at the time was AZT, okay? And they found that combining AZT with other treatments improve, right? Now, there were two candidate treatments to combine with, so DDL and DDC. And so if you notice, the response here is the CD4 cell count relative to the baseline. So it's just the ratio. And the idea is you want it to stay high, right? So if you look at just the AZT alone, just all the patients that took just AZT alone is obviously the worst of the three. The two combinations did better than just the one treatment itself. But if you look at the two combinations, there's no significant difference between the two combinations. So they're both about the same. I mean, the AZT plus DDL in this sample is slightly larger, but the standard error is they're clearly not different here. But maybe there are certain subgroups of patients that would benefit from one or the other combination, and we may be able to see differences there. So the goal of this study in the end is we're going to compare these two treatments, the two combination treatments, and see if we can find subgroups that might benefit from one combination versus the other. Okay. So before we go into that example, we'll go and talk a little bit about what the goal is here, okay, and how this is different than typical variable selection. Right? So if you think about what a typical variable selection method does, is it's going to consider variables that affect the response. Right? It's going to look for variables that are good predictors of the CD4 count. Right? So you'll have some sort of model, and you'll look at predictors that are good predictors for cell count, right? Which is a different problem than variables to help determine the treatment to employ. Right? Those are two different questions. And I'll give you a simple example of what I mean by that. And these are very simplified example here. So suppose I have three different variables of X1, X2, or X3, and just looking at them, they're on the range 0 to 1, and R is the response. And let's suppose here it's also on the range 0 to 1. If you look at X1, the first variable, we know that's a no interaction case, right? So here I have two treatments, A equal 1 and A equal 0 are the two treatments. And if I have, say, just a simple linear model here with the response and X1, I have obviously no interaction. I have parallel lines. And if I were to ask you, only knowing the value of X1, which treatment should you give? And obviously the answer there is, let's suppose here higher is better, right? The answer here is, regardless of the value of X1, I should give everybody treatment 1, right? Because I'm always going to get a better response on treatment 1, regardless of the X value. Now, X1 is a good predictor, though. For predicting the response, it's got a nice positive slope. So if I were thinking about variable selection, X1 would be a good predictor of the response. So I would pick it for a variable. But it's actually irrelevant for decision making, because it doesn't matter what level of X1 you have. Every patient should get A1, just using X1. Now you move on to X2. Now you see an interaction. But at least on the range of X2, which goes from 0 to 1, it's what we would call a non-qualitative interaction. The lines don't cross. So once again, if I said, which treatment should I assign? I should always assign it A equal 1. Okay? Variable X3, that's the variable we're looking for. Because if I look at X3, that's going to help me to make my decision. Treatment 1 is better than treatment 0 when X3 is greater than a half. Treatment 0 is better than treatment 1 when X3 is less than a half. Okay? That's the type of variable we're looking for. Because if X3 is bigger than a half, I assign 1 treatment, A1. If X3 is less than a half, I assign A0. Okay? But all 3 of these would be showing up in terms of variable selection for prediction, right? Because they all have nice non-zero slopes. They would be looking good for prediction, but only X3 is relevant for decision making. That's the variable we're looking for. And so the question is, how do I do that? How do I target decision making versus prediction? And so I'm going to define from those pictures what I mean by our formal objective here. And so an optimal treatment for a patient, obviously, is the allocation to whichever treatment maximizes the expected response, right? And that decision rule to make that optimal treatment is going to be a function of our variables X, right? So what we want to figure out is, give me the decision rule, which is a function of X, to yield the optimal treatment for each patient, right? Maximize that expected response, right? But our goal is to find the smallest subset of variables, let's call that X sub S, that results in the rule, right? Now, I don't care about prediction here, but I just want the rule, the decision, that matches the same allocation that the optimal treatment allocation does, right? These are the only variables that are going to be relevant for decision making. Right? That's formally what I'm looking to find, right? The smallest subset that results in that, essentially the same decision rule. Okay, so again, this is just exactly what I just showed before. The decision rule here is very simple, right? If X3 is bigger than a half, I give treatment 1, otherwise I give treatment 0. In practice, that's not going to necessarily be the simple decision rule. It might look something like this, right? A tree, right? I kind of go down the tree, and then I get at the bottom here, either the D or the Z, which you'll see later on is from the data that we were talking about. But in general, the idea is I want to find which variables are relevant for that. Right? Okay, so how are we going to do this? What is the common approach? Well, just do variable selection as usual, right? Do some regularization, do cross-validation, AIC, BIC. But again, the problem is that that's targeting prediction error, not the decision-making subset, right? If I'm looking at cross-validation, I'm I don't have the decision, the optimal decision as my observed data. My observed data is the response, right? So cross-validation is going to be over prediction error, things like that. Right? Well, if you think back to the picture that I showed before, we're looking for kind of interactions, right? So maybe I should just make a bigger model and just include main effects, include all the interactions, and only do variable selection on the interaction terms, right? Well, this is better because it's targeting sort of on the right thing, but it's still not targeting directly on what we want. Because if you remember that middle picture, that second picture, the two variables, the variable interacted with the treatment, but it still was not relevant for decision making, right? The lines weren't parallel, but they didn't cross, right? So it's better, and there are methods that do this second version, but it's still not targeting exactly what we want. The third approach is to use those pictures that I just showed and just look at things marginally and look for, okay, do these things cross? And where do they cross, right? If they cross just at the very end, it's probably not that important, right? The decision, you're only going to make it on a few people. And how much do they cross? How much, essentially, how much area is between the crossing points, kind of thing, right? And then they take these marginal things and they rank them based on these individual scores, and then they decide on where to make the cutoff. And that's another common approach that people have used. Obviously, we know the problem with that is looking at things marginally does not really give you the whole picture. So that's not exactly what we want to do either, right? We want to look at everything jointly. So here's what we're going to propose, and we're going to say we're going to call this no regret, and you'll see why in a minute. So let's assume for now that we know the true model and the true parameters in the model, okay? And what I mean by the model is the model for the expectation, right? So the model for the expectation of y given x and a, right? So in those pictures that I gave before, it was just a linear model and there was no interaction, or there was interaction, or whichever one it is. But let's suppose we know the true model, we know the true parameters, okay? Then this A star of x is going to be the optimal treatment rule. And the optimal treatment rule, so we're going to use a simple example here of two treatments only, right? So we've got treatment 1 and treatment 0, just like in the picture before. Now this can be extended to multiple treatments, so things like that, but for now we're going to do simplified notation and things like that to make it just two treatments. So the optimal treatment rule, if we know the true model, then the optimal treatment is just assigned to treatment 1 if the expectation given treatment 1 is bigger than the expectation given treatment 0, right? Just naturally, that's what it means to give the optimal rule, okay? Now this A star, it's a function, so it takes x and it's going to output either 1 or 0, right? It's going to output which treatment to go to. And it's a function of the true parameters, right? And it depends on the true parameters. It's a complicated function of the true parameters because it's an indicator function of an expectation, right? So the expectation could be a simple function, but it's but A star is an indicator function. All right. So what I'm going to think about now, based on that notation, I'm going to think about what I'm going to call the regret from using subset XS instead of the fully optimal model, right? So suppose I have the full model with X, and I'm going to take a subset and I'm going to think about how much regret do I have? And so the idea is for every patient, I'm going to think about what treatment decision policy can I get just on this subset? What's the best decision rule I can make just using this subset? And I'm going to compare the decision rule that I do for that patient. Plug in that decision rule, I get a response. And I look at what the optimal response would have been if I made the correct decision. Now, if the decision I make using the subset is the same decision as I make using the optimal one, then I get the same response. Right? So formally, and this is now, I'm defining a univariate parameter, right, that depends on which subset I decide on, right? So it's a single parameter for every subset I choose. Okay? And what I'm looking at here is, so if you look at this first, so forget about the outer expectation for now. Okay? Look at this first thing, it's the conditional expectation given I use the optimal decision rule. Okay? So this A star is going to be either 1 or 0, depending on which is best. So this first term is the maximum expectation I can get for a given x, right? I give you an x. This first term is the best I could possibly do because I'm making the optimal decision, right? The second term is the decision. I plug in A equal 1 or 0 based only on the information that I would get from that subset in terms of assigning treatment, right? So now if that subset was the whole set, then I'd make the same decisions, right? But in some cases, I could still make, so the ideal case here is, and then this, you think about this outer expectation, is just saying that, okay, well, I need to average this difference over the entire population, right? Or whatever my population of X is. And so this RS is a parameter. It's a univariate parameter that's a function of the parameters that are in my model, right? The true parameters in the model. Okay? Now, the idea, and this is why I say no regret, the idea is that I want no regret, right? Which is really a formal hypothesis test on this univariate parameter. Right? And what I said before is I want to find the smallest subset that gives me the optimal decision, right? This is a true parameter. If this parameter is 0, then that means I get the same expectation by using the decision rule on a subset as I would if I used the optimal decision rule. So this is mathematically what I defined before as the optimal subset. If RS is 0 and it's the smallest subset, then it's the optimal. Okay? So that's kind of where now I've defined formally a hypothesis test to decide whether this subset is essentially sufficient. Right? We'll see in a little bit is how we're going to use that hypothesis test to do variable selection. Okay? So think about, I'm going to go back to this simple example again because it's very easy to demonstrate what I mean by the regret. So again, the decision based on this full model, again, think about this as the true model with true parameters. So the decision based on the full model is x3 greater than 0.5, give treatment 1, otherwise treatment 0. Okay. So let's consider what happens if I removed x3 and I just considered the subset x1, x2. Right? So my question is, what is the regret from that subset if S is equal to x1, x2? Well, if I got rid of x3, then my decision rule is actually to always give treatment 1. Right? Because treatment 1 is always higher. Let's just assume this is an additive model I have here, right? Treatment 1 is always higher than treatment 0. So the decision rule is to always give treatment 1. So if I apply that rule, then what I would do is if you look at this right-hand panel here, if I were to apply this rule, always give treatment 1, then I would get this blue dashed line. That would be my response, that blue dashed line. But instead, if I were to apply the optimal rule, I would get this V, right? If I gave treatment 0 when x3 was less than 1/2, I would see this piece of the curve. And if I gave treatment 1 when x3 was greater than 1/2, I would see this right-hand piece of the curve. So my response for the optimal treatment, the response would be this V. If I ignored x3, my response would be this kind of 45-degree line going upward. So the regret is actually the difference between these expectations weighted by the population, right? So I would take this shaded area and weight it by the population density in this region. So this is just kind of the simplest case of what I mean by regret. Now, if we throw out x1 and x2 and we just kept x3, then I get the right curve, right? And so my regret would be 0, right? Because the expectation would match what the optimal expectation is. Okay. So this just kind of gives you a very simple example of what I mean by regret and how kind of graphically we can see that in the simple case. Obviously, in a standard case, you're not going to be able to see these simple things, but at least mathematically, it's well defined as a difference in 2 expectations. Okay, so how do we then do this hypothesis test? So I've got one parameter, and what I want to test is whether that regret is going to be 0. And so in order to do that, I need some sort of model. I have to have some model because this R sub S, if you remember, was going to be a function of the parameters in the model. So I need some sort of model. Okay. So what we're going to do is we're going to be flexible here, right? So we don't want to do a linear model. We want to do something more flexible. So we're going to use non-parametric regression for the response given each treatment condition. Right? Any one is suitable. So this is a kind of a general idea. So you can use any model you want. So splines or whatever you might choose to use. We used Gaussian processes in this case. So we assumed that each treatment condition, the expectation as a function of X was a Gaussian process. So we were very flexible in that. This is just an example. We'll see later on this picture again. So I just evaluated the Gaussian process on a grid of points, and this is actually averaged across all the other predictors. So just marginalizing all the other predictors out over age, and this is the kind of curves we got. What you look at here, obviously it's not a curve because I'm just connecting the points, but it's actually more, it would be a smooth curve. What you're looking at here looks as if here we have age, which would not be important for decision making, at least from this picture, right, as an example. And we'll come back to this later. All right, so the idea is within this general framework, now we have a model, we can imagine testing any pair of nested subsets, right? So I have a full model that is in some sense, my optimal decision rule, right? Because that's the best I can do. That's the most, I have the maximum number of predictors that I care about or think about, right? And then the idea is this subset, the subset that's nested underneath it, if RS is 0, it tells me that that reduced subset is sufficient for decision making relative to the full subset. Okay? So that's what we want to think about is just testing whether a particular subset is sufficient relative to the full model. Okay? And whatever I want to call the full model that's a whole nother question of what is your full model, but we'll talk about that a little bit. So again, the question is, how do I test this, right? And so, well, it's actually fairly straightforward once you think about it, is the univariate parameter, this one parameter RS, is a function of the parameters in the models, right? And so I could estimate that by directly plugging in the parameter estimates. Okay? It's going to be a complicated function because it's got an indicator function in there and things like that, but it's just a function of the parameter estimates from the model. So in our Gaussian process case, it's a function of there's the correlation parameters and things like that in the covariance function for the Gaussian process. So it's a function of those things. In splines, you've got the regression coefficients on the splines, right? So whatever your parameterization of your model is, it's a function of those. So you can plug in the parameter estimates. And we also know we have asymptotic distributions, right? So you think about the asymptotic distributions of your parameter vector in your model, right? And it's a transformation, right? So we could think about doing a kind of delta method type idea to transform from this multivariate joint distribution to a univariate distribution, right? It's not a very straightforward transformation. I'm not going to go into the details here. There's a lot of details that are how to actually do that transformation, what it is, but it is just a transformation of the original parameter vector. And we use the ideas, just delta method ideas. Okay, so an application of this, and this is where the variable selection is going to come in, is to do, once I have a way to test for a subset, I could do forward selection, I could do backward elimination, right, and use kind of p-value type stopping rules. Right? Once I have a hypothesis test for can I reduce to this subset, right? Or do I need to, if I go forward selection, it's okay, do I need to add this next variable, right? That adding the next variable is the full model, where I am now is the reduced model, right? Or doing backward elimination, well, can I remove that variable? Well, that's the subset that I'm interested in. So once I have a way to test a subset compared to a full model, then I can just embed that within a kind of a stepwise procedure. So we're going to use here in this application, we're going to use backward elimination. And I'll talk a little bit later about why we particularly chose backward elimination here rather than a different choice. So really, it's quite natural how to do it now, right? First step is you estimate the parameters in the model. The second step, you now have predicted response for each treatment. So you have an estimated treatment rule, right? And then you just go ahead and you remove one predictor to get the reduced subset, redo the estimation, you get the reduced model, and then you can directly compute the regret, right? You have all the pieces that you need to compute the regret that I talked about before. And then again, obviously, just like backward elimination, you look at removing each one variable at a time, and you find the one that has smallest regret. And then you keep going, repeating further down until your stopping criteria is met, right? And what stopping criteria? Well, now we know how to test for whether I can reduce down or not, right? That was, if the null hypothesis RS was 0, then that means yes, I can reduce down, right? And so I keep going until I'm no longer able to reduce down, right? Just a standard backward elimination procedure. The key here is understanding that we're testing for a parameter that's very different than a typical regression parameter, right? We're testing for this R, this regret parameter. Okay, so I'm going to go through this example here a little bit now. And so again, this was this 2 combination treatments. The first one was best on average, but again, just by a little bit, so not really best significantly. And so again, we have 16 candidate predictors here. And so I'm going to use the 16 predictors in the backward elimination. And so as I did that, we went all the way down and ended up removing 10 down and keeping 6 in the model. The next one, so in this table, I've got p-values. And so what I have here is a Bonferroni corrected, just because at each step, like for example, the first step, I'm looking at 16 different models. So I just correct by looking at 16 tests, and just a simple correction there. So what I have in this table is these are the 6 variables that stayed in the model. And what these p-values are representing is I have this model of size 6 that I'm down to. And what if I were to remove this first variable, the number of days of previous therapy, and consider the full model as this model size 6, and the reduced model, the model of size 5 after removing this first variable. And my p-value is about 0.01. So what that's saying is that the reduced subset is not sufficient. RS, if I remove this first variable from the 6, RS is not 0. Right? So I can't remove this one. And so that's what these p-values represent, is for each of these variables, what if I were to say, well, can I remove that from the set of 6? And the answer for that is, this is my last step. I can't remove any of these. The step before, the p-value was 0.2. The last thing I removed was 0.2. Right? So there was a big jump in a 0.2 versus a 0.01. That's the next one. All right, so these are the 4 variables that came into play. Now you may remember I showed a plot before with age, which looks to be highly important here, but I showed a plot that didn't look like age would be relevant. And here's that plot again. And so here again is age. And so what I am again plotting here is the 2 different treatments. So what the main effect of age would look like in the 2 treatments. So I've used this Gaussian process regression, right, for each treatment, and then marginalized out over all the other covariates. So this is essentially like the main effect of age, right, in the 2 treatments. And then another one that showed up there was whether or not they had prior usage of this ZDT. Right? So whether or not they had prior usage, again, it doesn't look like there's an interaction, but it doesn't look like it'd be relevant for decision making, right? For decision making, it looks like I should always give this top treatment, right? The DDL. Right? And same thing here. So in both cases, it looks like regardless of age or regardless of prior usage, I should give DDL. So why are they showing up as really important? And that's going back partly to what I was saying before, is looking at things marginally don't always give you the full story. So what I'm plotting here is looking at the interaction between the age and the prior usage of ZDT. So those 2 variables that I just had on the previous page, I'm now stratifying on age by the value of the prior usage. And so on the left here is when prior usage is 0. So what you see here is that there's some weird kind of dip, and this kind of peak over in the end here on this this dashed line is probably an artifact of very little data. So if you look at this, this is kind of the density plot of the actual data that's in this subset. And so most of them are kind of in this 30 to 40 range. So this kind of peak at the end here potentially is an artifact of not having much data. But what you look at is, in this case, it looks like the DDL component is probably best for everybody. There might be a little bit of crossing over in this small little region here, but in general, it looks like I should give everybody here DDL. But if you look on the right-hand side, it looks like there's a region here that should get the other treatment. And that region, again, if you look at the density plot, that region is a fairly high density region, right? So it's not like this crossing is, you know, a couple of patients here and there. There's a large number of patients in that area right there. So looking now here, then maybe there is some combination that would be better to give. So again, it looks like there could be some subgroup that might benefit from the other treatment. So what I've done here now is to go back and think about, how do I validate our treatment decision, right? So I'm using a cross-validation study to evaluate the treatment policy. And so what we're using is what's called the value of a policy. And this is a common way to evaluate policies. And so you do the holdout data and you compute the mean response on the holdout data for those observations in the holdout data that are consistent with the treatment policy. Otherwise it's zero because they're not consistent with the policy. And this is a common way that people in the idea of personalized medicine evaluate these approaches. And so I average this over 100 splits of the data with the standard errors there. And so what I'm looking at is, what if I gave everybody, so the first row is, what if I gave everybody the one that was slightly better, right? So in other words, 100% of the patients are treated with this DDL. And I get a 9.4 value increase, and this is relative to everybody getting the other treatment. Okay? So I get a slight value increase of 9.4. Okay? This essay is what's called sequential advantage. It was a 2016 version, and what they're essentially doing is looking at variable selection on interactions. They do it in a very non-parametric way and a sequential kind of way, but it's essentially doing variable selection on interactions is the main idea behind it. And then this NP is the non-parametric regression approach that I'm posing here. And if you notice the policy, the percent of the patients treated with the DDL is about 50% from both policies, but it turns out they're a very different 50%. So they both treat about 50% with the two drugs, but there's a very little overlap between them. It's probably, I think it's about less than half overlap between them. And what you notice is that going through this whole process of coming up with a personalized treatment, giving about half the patients one, half the patients the other, using the sequential advantage approach, really didn't give much of a benefit, right? The value is essentially the same as just treating everybody with the DDL. So it didn't really find what we would consider that great of a policy. Whereas ours, it's a much more relevant difference. All right, so the next question I would ask is, well, how would somebody use this in practice, a medical professional? Right? So imagine what they would do. So I have this Gaussian process, complicated model going on here, and they would have to, so they have to have a black box, right? I'd have to give them this software and they'd have to say, okay, input these patient values, computer would spit out, here's your best treatment. They may not appreciate that, right? They may want some interpretability, right? So what we've done here then is from this analysis, is we've taken the results from this estimated policy, and we're going to turn it into a decision tree. And that's what the decision tree that I showed earlier. Right? And the idea is I have my Gaussian process, and now for every patient, I now have a 0 or 1 as to which treatment is better, right? So I take my Gaussian process, which I have 2 Gaussian processes now, right? And for each patient, I turn it into a binary, right? So now I have binary data for each patient because I know what the decision for my Gaussian process would be. So I have binary data now for each patient. And then what I do is I just fit a decision tree to that. So it's essentially a decision tree approximating this model. Right? And then this gives us kind of a visual representation. It's not going to be exactly the same, but it's the best approximation a decision tree is going to give me. And this is that decision tree that I showed earlier. And so the idea is that, okay, if you have a lower CD4 baseline count, you go to the left. If you have a higher one, you go to the right. Race showed up, important age showed up, right? And then this on the left here, you see the prior ZDT use is no or yes, and then age shows up there. That was kind of that interaction between the prior usage and the age that we saw that was important. So that's kind of showing up in the left-hand combinations here. So this is kind of, again, a visual, something where a physician can maybe interpret things here and have a little bit more confidence in the method, not just spitting out a black box decision. Okay. And then the last thing I want to just talk about, let's see, so we got a little bit of time, I think, right? So the last thing I just want to talk about is I did backward elimination here, right? Again, that's not necessarily the thing to do, right? The idea was I come up with a hypothesis test method. Once I have a testing approach, then I could embed that into other things. But one question could be, well, with backward elimination, 16 variables isn't too bad, right? But what if I have a really large number of predictors? Backward elimination is probably not going to work very well with a huge number of predictors. So maybe not, why backward elimination and not, say, forward selection, which with a large number of predictors might work better, right? And so the first one is sort of straightforward. So what we can do, and we did this kind of in some simulation, is to first do a screening method to reduce the number of predictors, right? And so you just go into each group separately and you do a screening method. And when I say screening method, I'm screening for standard variable selection. So here I think about doing standard predictive variable selection. And the reason is if a variable has no predictive power in either group, then that means they're flat, right? So they can't have the type of interaction that we are looking for because they're flat in both groups, right? So you can just use a standard variable selection screening method for prediction purposes to get down to the variables that have predictive power in at least one or both groups. And those are the only ones that can have interactions as well. Right? The second question is a bit more subtle. And the reason I say it's a bit more subtle is because there's some computational issues here. Right? So first you can think about, for forward selection, you think about adding one variable at a time, right? And so what you need to do is you need to fit a model for each candidate subset that's obtained going forward, right? And then you need to do that at every step. Now fitting can, in many cases, be done in parallel. So this may not be too bad of an issue, right? If you do, because you're fitting the separate models, you fit them in parallel, it may not be such a bad deal. For backward elimination, I need to do the same thing. So the question is what's the difference here? Why am I saying that backward elimination can be more efficient than forward selection? And the reason is I could actually use an approximation to backward elimination. And we did this, and it came out, the results were essentially almost identical to doing the full process. And the idea is you start with just the full fit, okay? Again, we've already reduced down by screening. So you start with the full model. And now you have the joint distribution of the estimated parameters. From that alone, I can approximate what results I would get on any subset of that. So I only have to fit the full model, and I can approximate any reduced subset. Because removing a variable from the model is just going to be equivalent to setting some parameters to 0, right? So if I have a known joint Gaussian distribution to start with, I just condition on the appropriate set of parameters being 0, and I get a conditional Gaussian distribution that has a known form, and I don't need to refit at all. Right? So I can, if I fit the full model, then I can get any reduced model, at least approximately, by using this conditional argument. And so that's actually what we did here, because Gaussian processes are very expensive to fit. If I have to fit so many of them, I could do it in parallel, but here we actually did both and found there was much difference. Okay. And so kind of just end here with just a kind of a quick, so obviously the benefits, obviously we can look at targeting relevant for decision making versus prediction. And it could also, again, it can apply to multiple treatments, right? The idea is instead of looking at just a difference, you look at a maximum. That's just notation gets a little bit tricky. Now the question is, what I really want to look at is dynamic treatments. And so I haven't done that yet. So this is just a static one time point decision, right? Which treatment do I give? But ideally we have multiple decision points. And that brings up a whole lot of questions. First of all, which variables do I use to make a decision? Which time points do I look at? What triggers making the switch? There's certain variables, certain combinations of variables, certain kind of improvements or adverse effects, or there's lots of different things that have to go on there. And so that's kind of an interesting thing that I'd like to think about. I'm not 100% sure on how to start, let's put it that way, but so I guess I'll end here and then take questions.
Oh, well, thank you, Howard. That was a really interesting talk. I guess the way we'll sort of do questions is people can basically unmute and ask, or if you want to use the chat, you're also available to use the chat option. So please feel free to ask questions for Howard.
Francis, this is Xuming Tam. I enjoy Howard's talk. I just have two silly questions. The first one is that step 1 of your slide 15. What does that model look like? Do you build that model based on, say, machine learning or artificial intelligence methods? So that's the first question. And related to that is that you got an expectation over X to calculate the regrets. So you treat X as random variable, whereas in classical statistics, when you're looking at those predictors, you treat them as constant. So I wonder if you could also explain a little bit about that.
Yeah, so your first question, the parameters in the model, so you mentioned a machine learning kind of method. You can use a machine learning method, that's fine. We use the Gaussian process model. Right? So it's really any method you use. So I mean, in our case, the model is just you have model for the expected value of y given x and a. And you can do whatever you want. You can do machine learning. You can do, I mean, you could do a linear model if you wanted to, but that's probably not going to be flexible enough. So it really could be anything. Now, the problem comes in if you do some sort of machine learning method, getting that asymptotic distribution of the parameter estimates is not typically well known. So that would make potentially some issues. So you probably want to use a model that has asymptotic results that you can use. So on the second question with the expectation, so it could be either way. You can think of x, that expectation over x, this outer expectation, as thinking about the population distribution of x and actually taking a expectation over the population, right? So then it is thinking about x as a random draw from the population, but you could also think about it as x being fixed, and this expectation is just the sample average over your data values, right? So it's the expectation that just, where the distribution just puts all its mass on your data, right? So it's just a sample average then. Does that answer the question?
Yeah, thanks a lot. Thanks.
Can I ask a question?
Sure.
Yeah, hi. Yeah, so it's a very interesting talk. Thanks for pointing out the big difference between variable selection for prediction and for the purpose that you talk about. You've talked about regret as a comparison of the optimal A star with an A star based on a subset of variables, not the full set. If you can compare both the optimal A star and the A star based on a subset, why don't you just simply pick the optimal A star as your solution?
So the optimal A star is based on all of the variables.
Yes.
So that is the optimal solution. But what we want to look for is, can I get the same decision rule with a smaller subset?
What would be wrong with simply using the optimal A star? What's the disadvantage of using the optimal A star if it's optimal?
Well, it's the kind of thing where, so imagine you have a regression model.
Yeah.
And you have a huge number of predictors in the model, and a bunch of the coefficients are zeros.
Right.
But that still is the optimal model, right? That's the way the betas are zero, right?
Right.
But in reality, what that means is that you really don't need all of those variables. You can throw some away and just use a smaller subset.
Right.
And so this is the same idea here, right? If I can make the same decisions as what I would do in the expanded set,
Right.
again, knowing the true model, then it's like saying I've got parameters that are equal to zero. Right?
Okay. Yeah, thanks for that answer.
Howard, there's also a question in the chat.
Okay. I'm not sure. Maybe I need to maybe stop the share. There we go. Okay. Yeah, I couldn't see the chat with my screen being shared. Okay. So the question is, how would it translate where there are multiple outcomes and the importance of each outcome may differ? Ooh, that's a tricky question. I'm not sure. I guess the question is, so if you have multiple outcomes, I think the idea would have to be that you would have to somehow combine those outcomes to a single outcome, to use what I'm talking about here, right? And so maybe it would be multiple outcomes, and there's a certain weight on survival and another weight on quality of life, that kind of thing. But you'd have to somehow combine them into some sort of expression from an outcome. I think is, in order to use directly what I'm talking about here, you'd have to combine them into what you believe is the outcome of interest. And I think that makes sense.
Any other questions for Howard? I guess if people don't mind, I mean, I'll ask one sort of maybe a bit of a silly question as well, which is that you sort of mentioned at some point for sort of making this thing communicable for sort of doctors and GPs that or the medical profession is sort of having a sort of essentially using a tree to try and sort of visualize the decision making. And so I guess the question is, could you actually start with a tree and try to actually build the process directly from that?
So the problem there is that you don't have the 0-1 data to feed the tree, right? And that's where the question comes in, right? So what's the data to feed into the tree? And so in this case, we've created the 0-1 data that can then get fed into the tree.
Okay, thank you. Any other final questions or comments or thoughts? If not, then thanks to Howard for giving a very, very interesting and intriguing talk, and thanks to everyone for turning up. And yeah, I guess this sort of concludes the meeting, and I guess we'll see everyone, see you all at the next meeting. Thank you very much.